Hey there, this is the lecture for section 4.5, graphs of logarithmic functions. All right, the graph of the logarithmic function is always going to take the same basic shape that we have shown here, right? We see the red graph is log base 2 of x, the green one is the natural log of x, and the blue one is the common log of x, or log base 10 of x. So interesting things to note is we can see that as base increases, the graph becomes just a little bit flatter, right? We always will have a horizontal intercept right here at the point 1, 0. Why would that be? Well, recall that the logarithm is the inverse of the exponential function, right? So that means that the graph of the logarithm is going to be a reflection about the line y equal x. Right, the black one that I just put in here, that would be the graph of 2 to the x. So we can see that the red graph, log base 2 of x, is a reflection about the line y equal x of 2 to the x. Right? So the reason that we always have a horizontal intercept at 1, 0 is because it's the inverse of the exponential function, which always has a vertical intercept at 0, 1, right? Recall that inverse functions swap their domain and range, right? Or they switch their x's and y's. Inputs become outputs of one, and then those outputs become the inputs of the other. Okay, so there's a vertical asymptote at x equals 0. We can see that right here, and that makes sense, right? Because on the exponential function, we have a horizontal asymptote at y equals 0. Okay, logarithmic graphs will always be increasing without transformations, of course, increasing and concave down, all right? And the domain of the logarithm is going to be 0 to infinity, right? Which makes sense because the range of the exponential function is 0 to infinity, right? The range of the logarithmic function, is all real numbers because the domain of the exponential function is all real numbers. All right, let's talk a little bit more about the domain. All right, if we wanted to find the domain of this first example, the log of x plus 2, think about what's happening as far as transformations go there, right? Like if I were to sketch common log of x, it's something like that, right? Well, what transformation is happening here? It's a shift left 2 units, right? So it means this asymptote, the vertical asymptote, is shifting left 2 units because that whole graph is shifting left 2 units, right? So the whole domain just shifted left 2 units. So what is that domain going to be? Instead of negative infinity to 0, it's going to be negative infinity to negative 2. All right. Now you can always just find this domain using algebra because we know that the argument of the logarithm put to the logarithm has to be positive, right? That's our domain for transformations, greater than 0, positive. So algebraically, we can just do this. We can just say that the argument, x plus 2, has to be greater than 0 and solve for x, right? So x has to be greater than negative 2, oh gosh, I wrote that backwards. That's not negative infinity to negative 2. That's negative 2 to infinity. You must think I'm crazy. There we go. Negative 2 to infinity. We're going off to the right. We're not going to the left. So there we go. All right. Look at this next one. Okay. There's 2 transformations going on here, right? We got a horizontal reflection plus 5. So that's going to be a shift left 5 as well. But I don't need to worry about it. I can just look at that algebraically. I can say that 5 minus x has to be greater than 0, solving for x, right? So negative x has to be greater than negative 5. And then maybe you can multiply or divide both sides by negative 1. Well, when I do that, right, I got to flip that inequality, right? So then x is less than positive 5, right? So my domain here is going to be negative infinity. Yes, this time it is negative infinity to 5, right? Make sense for transformations? Yeah, think about this. We're going to reflect it, right? Reflect it and shift it. But with the reflection, with the horizontal reflection, we're going right. Okay, one last thing. One last one in here. Look at that domain. That's just a horizontal reflection, right? Flip him over. So that's going to be negative infinity to 0. But I can always solve for that algebraically. I say negative x has to be greater than 0. Divide both sides or multiply both sides by negative 1. Flip my inequality. And there's my domain, negative infinity to 0. All right. Let's talk a little bit more about transformations, right? Because transformations result in some really cool things with logarithms. Okay, remember that change of base formula? Log base b of x equals log base c of x divided by log base c of b, right? We use that if we want to maybe convert a funky base to common log or natural log, something like that. Well, think about that for a minute, and then factor out 1 over log base c of b. So what I'm left with is 1 over log base c of b times log base c of x. What this does, this tells me that I don't ever have to worry if I'm graphing. I don't have to worry about what the base is. I can always write it as a vertical stretch or shrink of a common log. Does it make sense? Look back here at these graphs. Look, base 2, base E, base 10. Don't they just look like a vertical stretch or compression? Yeah, so that's kind of cool. Another cool thing is if you apply a horizontal stretch or compression to a logarithm, right? You could then use the sum of logs property. If you have log base c of x, you could rewrite that as log of c plus log of x. So what does this mean? It means we never have to worry about any horizontal compressions or stretches because it's the same thing as a vertical shift, right? So because of that, then the standard form that we can use for transformation of logarithms is a little bit easier. We have two versions of it. The first one is when there's no horizontal reflection. It just says it's a, that's our vertical stretch or shrink, right? Times the log of x minus b. B, that's going to be our horizontal shift. And then plus k, where k will be our vertical shift. Okay. If we have a horizontal reflection, though, we'll use the second version, a times log of negative, in parentheses, x minus b, and then plus k. All right. B is always going to be our vertical asymptote, right? That's always going to be our horizontal shift. Okay, so let's look at some examples, see if we can write the equation for these graphs. All right, so we'll work with our standard form. F of x equals a times the log of x minus b plus k. Unless we have a horizontal reflection, then we'll use the second version, which is a times the log of negative x minus b plus k. So look at this first graph. Well, let's see what reflections are going on. I like to visual. Let me put it on there. There's that dotted line. That's a logarithm that has not been reflected. Okay, so compare that to the blue one. Let's think. I think it looks like there's a vertical reflection. I don't think there's a horizontal reflection, just a vertical reflection, right? So that tells me I want to use the first version of the graph. And it also tells me that A is going to end up being negative, right? All right, now what about the horizontal shift? That's always easy to see because, you know, the vertical asymptote is easily observed. We could see that the vertical asymptote is at x equals negative 3. So that means my B is going to be negative 3 here, right? So I can kind of start writing my function. Let's see. I can put the B into it anyway, but how do I figure out what A and K are? Well, to find A and K, I'm going to use clear points on the graph. When I say clear points, I want to try to find whole numbers that I can work with. And the horizontal intercept is always a good one to start with because one of those values will be 0, and that may make our calculations easier. All right, so I'm going to use this point with the coordinates -2, 0 for x and y. All right, I'm going to substitute that in for x and y in my standard form, and I'm just going to see what I've got. All right, so if y is 0, means f of x is 0, so I'm going to say 0 equals a times the log of x minus b. B is -3, right? So that's going to be minus -3, and then plus k. Oops, I didn't mean x. I wanted to put the value for x in there. Sorry. I'm getting going here. Forget what I'm doing here. The value we're using for x is -2. There we go. All right, so let's simplify. That's simplify. A times the log -2 plus 3. It's really just log 1 plus k, right? What is the logarithm of 1? What exponent would I put on 10 to get 1? It's just 0, right? So that made things pretty easy for us. 0 equals a times 0 plus k. What does that mean k is? K is just 0. So that tells us that this graph does not have a vertical shift, right? It does not have a vertical shift. I can forget about the k. All right, so now what? Where do I go from here? What do I have so far? Well, let's write what we've got. F of x equals a times log x. There, to make it general again. It's going to be x plus 3. We'll put it in its simplified version. Okay, that's what we know so far. We know k is 0, and we know that b is -3. All right, so now what can we do to find a, to find our vertical stretch or compression? Well, let's just pick another clear point, a clear point being one that has whole numbers. I like this one here that has an x coordinate of 3 and a y coordinate of -3. All right, let's plug that x and y into our equation and use those numbers to solve for a. All right, so y is -3, so we're going to say -3 equals a times the log of, and x is 3. So 3 plus 3. All right, that's log 6. Now, if I want value of a, all I need to do is divide both sides by log 6, and there's my a. Okay, so I can write my full equation now. It's f of x equals a, which is -3 over log 6. Does that make sense? Yeah, it was supposed to be negative, right? Because we had a vertical reflection. -3 over log 6 times the log of x plus 3. No, not enough room on this slide. Should make it bigger. Should we try another? Ooh, this one looks interesting. All right, let's think about our reflections. So there's what that logarithm would look like if there weren't any reflections. Do we have them? Oh yeah. We have, I think we have 2 reflections. We have a vertical reflection and a horizontal reflection, both. Right? So our A is going to end up being negative here from the vertical reflection, but we've got a horizontal reflection as well. So now we want to use the second version of our standard form that accommodates that reflection. All right. So what is our B here? There it is. B is going to be 3. We're shifted to the right. All right. So B is 3. So let's see what a clear point. Let's use our horizontal intercept to start. Value 2, 0. So there's an x and a y that we can substitute in. All right. So we'll say 0 equals a log x. Oops, no, it's a horizontal reflection, so it's negative x minus 3. Right, that's our, and then plus k. What am I doing? I forgot to put my x in there. My x is 2, so it's going to be -2 minus 3. There we go. All right, let's just simplify. 0 then equals a times the log of 2 minus 3, that's negative 1. Oh, this is just a log 1 again. Well, that's nice. We have another example here where k is going to be 0, right? Log 1 is 0, 0 times a is 0. So we now know that k is 0. All right, so no k, that's just 0. Let's pick a second clear point and solve for a. All right, so let me just rewrite it. We have a times log of negative x minus 3, the k is 0. Now let's pick another clear point. Let's see, I think I like this one right here. It looks like it's most on the intersection of those grid lines. So the values there, the x is negative 2 and the y is 4. All right, let's plug those in. So instead of 0, I forgot to put this back the way it was supposed to be. That's an f of x. All right, so instead of 0, we're going to say, let's see, it's y is 4. So 4 equals a times the log of negative, x is negative 2. All right, so it's going to be negative of negative 2 minus 3. All right, and let's simplify that. 4 is equal to a times the log. All right, negative 2 minus 3, that's negative 5. The negative of negative 5 is a positive 5, so it's a log 5. Okay. Oops, I brought a negative sign on the 4 as well. Sorry about that. That's negative 2, negative 4. All right, solving for a, we just divide both sides by log 5. And we can write our equation now. F of x equals negative 4 over log 5. Let me write it there. Let's try this. I better write it up here. F of x equals negative 4 over log 5 times the log, I don't really need to put that in parentheses, times the log of negative x minus 3. Okay, let's try one more. Okay, well, it looks like we don't have any reflections going on. That's nice. We just have a shift left. Isn't that what that looks like? And it looks like the asymptote shifted over to here. So our b is negative 4. Our b is negative 4. The reflections, they always get me, but this is not going to be too bad, is it? All right, so what do we have? F of x equals a times the log of x minus a negative 4. So that's an x plus 4, and then plus a k. All right, the clear point. Let's start with our horizontal intercept here, negative 3, 0. I don't want to forget negative again. Okay, negative 3, 0. So then 0 equals a times the log of negative 3 plus 4 plus k. Oh, we have another log 1. Am I doing this wrong? 4. Oh, I think that's right. So 0 equals a log 1 plus k. If I subtract k from both sides, I still have a k equals 0 situation here. No shifting. Can that be right? Yep, I guess it can. All right, so now let's take a look at another clear point. Oops. How about if we use this one, 1, 3. Let's erase. We know k is 0, so we can forget that. All right, let's put that point in there. 3 is going to equal a times the log of 1 plus 4. That's log 5, right? So dividing both sides by log 5, a is going to be 3 over log 5. Okay, so here's our equation. F of x equals 3 over log 5 times log x plus 4. Okay, that ends the lecture for section 4.5.